All right, AP Environmental Science. Today we are going to cover topics 6.1 and 6.2. So we are starting Unit 6 today. Unit 6 is all about energy, which is a pretty big topic that'll be covered on the AP exam. And we're going to talk about a lot of different aspects of energy, energy consumption, different types of energy, different resources that we use to obtain energy. And finally, we'll talk about conserving energy because it's a really big issue facing the world today. So we're going to start today talking about this term non-renewable. We've talked about this briefly before. A non-renewable energy resource is something that we're going to run out of. This word here, finite, this is kind of the opposite of the term infinite or infinite, which means that we don't have a lot of it. I mean, there's some good examples are things like coal and oil, natural gas, uranium. These are all things that we have to either mine for or drill for, but we don't have a lot of them. So, and also, we've been drilling and mining for this stuff for a really long time. So, the chances of us running out of these supplies are getting pretty serious. So, the thing about these non-renewables is most of the countries around the world are extremely dependent on them for energy. So things like coal, for example, a lot of the electricity in the United States is generated using coal. So, if this is something that we're gonna maybe run out of someday, maybe one day we're gonna have to figure out some type of alternative to coal, and we're already kind of there. We're already kind of looking for those things and even implementing those things. A couple terms here: fossil fuels. A fossil fuel is a non-renewable resource that we basically get from some biological material, either plants or animals that have died. We'll talk about that process eventually, but eventually they became fossilized and they form, these fossil fuels that we can now obtain from the earth, and we could use those things as energy. There's lots of energy in fossil fuels. Nuclear fuels, these are things that are derived from radioactive materials. The most common one is uranium 235. Again, we have to mine for that. And once we obtain it, we can use it to generate energy, nuclear energy, which there's a lot of nuclear power plants in our country that utilize that type of energy. All right. One thing I do want you guys to sort of be aware of, because we will be doing some math in this unit, is units of energy. There's lots of different units of energy. The one that we're probably going to be utilizing the most in this class is a unit that you probably should be somewhat familiar with back from your chemistry days, and that's the unit of a joule, Joule. It has this abbreviation, capital J. This is just the basic unit of energy. Calories is another one. There's several different units that we can use, but this is the one that we're going to use for the most part. Now, a joule is a really tiny unit, like really small. It's like, if you were going to measure, I don't know, the distance from Chicago to Miami, Florida, all right, you probably wouldn't measure it in centimeters. You could, but you probably wouldn't, because the centimeter is really a small unit and you're measuring a really long distance. You probably would use like miles or kilometers or something like that. Now, in energy, a joule, again, it's the basic unit, but it's a really, really tiny unit. When we're measuring energy and looking at like global energy use and things like that, we typically aren't going to use this little unit. Instead, we're going to use something called a gigajoule. A gigajoule, GJ is the abbreviation there, is a billion, or 1 times 10 to the ninth, of these units. Okay, it's a billion joules. Now, a gigajoule is about the amount of energy that we can get from 8 gallons of gas. If that kind of puts it into perspective a little bit more for you. But even that unit, a gigajoule, is a fairly small unit, even though it's got that prefix giga in front of it, and it is a billion joules. It's still kind of a small unit. This term here called an exajoule. An exajoule is a billion gigajoules. So it's 1 times 10 to the ninth of these units, these gigajoule units. Now, that unit is a lot more useful when we're measuring like global energy use or how much energy is used by, let's say, a country. We'll look at some graphs in a few minutes that have exajoules as units. But, an exajoule is basically this many, which is 1 times 10 to the 18th of these basic energy units called joules. All right, so this is a slide here that I don't think it's that hard to understand, but it's something that we probably should understand if we're going to do math and converting from one unit to the next, utilizing these types of units. All right, now globally, we're going to look today at some different slides and look to see how energy is used around the world. There's a term here, it's called commercial energy source. A commercial energy source is basically anything that can be bought and sold. For example, coal and oil and natural gas, we mine for these things. Sorry. We drill for these things and then we sell them, right? I mean, these are commodities, I mean, oil companies are, billion-dollar companies because not only do they access the oil, but they sell it to other people and to other countries, right? So this is a commercial energy resource. Now, the term subsistence energy or subsistence energy resource is something that you can just go out and gather on your own and you can get energy from it. A good example is firewood. If you want to go out and gather some firewood, chop down a tree, bring it back to your house, put some firewood in a fire pit in the backyard, have yourself a bonfire, roast some marshmallows, you're more than welcome to do that. That's not necessarily a commodity, even though firewood, I guess, could be bought and sold. But you can just go out and obtain it on your own, right? Now, the thing about commercial and subsistence energy use is different countries around the world utilize these resources a little bit differently. For example, in the developing world, countries that let's say are in stage 1 or stage 2 of demographic transition, there's a lot more subsistence energy that's used in those countries compared to commercial energy, probably because of the price. I mean, a lot of people in these countries just can't afford some of the commercial energy resources in order to utilize those things for energy. Here's a good statistic here. It says 20% of the world's population lives in developed countries, and they use 80% of the world's energy. So if we're looking at energy usage, globally, we have to really look at the developed world because we're the countries that are using most of that energy. But again, I go back to this demographic transition model. We've got more and more countries that are moving from, let's say, stage 2 to stage 3. So if these countries are shifting demographically, then there's going to be a shift in energy usage. We're going to go from countries in stage 2, that uses a lot of firewood and charcoal and things like that to heat their homes, for example, to all of a sudden being a stage 3 country where those countries are using a lot more commercial energy. So there is a shift. Whenever you see that demographic transition model, there's a shift in energy usage as well. Now, globally, this pie chart here, I kind of want you to understand this. You can see a couple different pie charts today. This is just showing you global energy use. The total here, and this number does change from year to year. This is the number that we had from last year. It might be a little bit out of date, but 570 exajoules. This is how much energy the world uses, on average, all right, or close to it. So 570 exajoules. And how are we using that energy? Kind of breaks it down here for you. These first three chunks of the pie here, this 81%, this is fossil fuel use. So 81% of that 570 exajoules is just utilizing fossil fuels, burning coal, burning natural gas, burning oil or gasoline, which is petroleum, for cars and things like that. 81% of our energy use comes from fossil fuels. Now, 14% of it comes from what we call renewable energy, which we will talk about eventually. Things like wind, solar power, tidal power, that type of thing. We'll get into that stuff, but only 14%. But the good news is that that number is on the rise, and this 81% is actually declining, which is a good thing. 5% of our energy comes from nuclear power or nuclear fuel. All right, so we're going to talk about every single one of these sort of in detail as we go through this unit. This graph here shows you a couple of things. You've got the purple bars and the blue bars. So let's first look at the purple. The purple bars represent total energy consumption, and it breaks it down by country. It doesn't show every country, but it shows you some different ones. The two that I think kind of stand out are China and the US. China uses about 130 exajoules. They are the world's leader in energy consumption and energy use. The United States is fairly close behind, about 103 exajoules. So if you kind of add those up, that's about 230 exajoules. That is about 40%, going back to this, it's about 40% of the total world's energy use. So think about that. 40% of all the energy that's used in the entire world is used in two countries, okay, China and the US. So if we're really serious about studying and looking at how energy is used, we kind of have to look at those two countries pretty in depth. And we're going to look at those two countries, especially ourselves, especially the US. Now, the other bar here, the blue bar, is per capita. And that's per person. Now, this is given in gigajoules. It's a smaller unit because we're going from an entire country to the individuals that live in that country. So if you look at the blue bar, the average US citizen, so you, use about 325 gigajoules of energy each year. Remember, a gigajoule is about the amount of energy in 8 gallons of gas. So you use about 325 of those gigajoules every single year. China, the world's leader in energy use, take a look at what their per capita use is. It's only about 75 gigajoules. If you look at the bottom here, okay. So that's about the world's average, about 75. So, if we're talking about energy use, as a country, I think China has to look at themselves basically because they have so many people. That's why their global or their total use is so high. But in the US, not only is our total energy use high, but our per capita use is high. I mean, we use more energy per person than any other country on the planet. And it is a big problem, but a lot of it deals with our lifestyles, and kind of what we feel is important, right? We all drive cars. That goes into energy consumption. We all plug in our cell phones and watch Netflix and all these things. It all uses electricity. So that all goes into our energy usage as well. So lots and lots of factors go into these numbers, but India and China have some different issues, all right, some different ways to look at things. All right, now in the United States alone, again, we mentioned that the US uses about 103 exajoules per year. So if you look at this graph on the left, this graph is a little bit different. I'm going to go back to this real quick. A little bit different from this one. This one is the world's pie chart, the whole world. This one here is just the United States. Okay, so the numbers are a little bit different. Again, though, about 81% of our energy comes from fossil fuels. You'll notice that the renewables a little bit less than the rest of the world. The nuclear is a little bit higher than the rest of the world. But 81% for fossil fuels is about the same as what the rest of the world is using. We just kind of use it in some different ways. For example, these percentages of oil, coal, and natural gas are a little bit different from the rest of the world. But how are we using our energy? Mainly four things. And the world does the same thing. It's just maybe different chunks of the pie. We use it for transportation. We use it for industry, commercial, like our stores and businesses, and residential. We use energy in our homes. All right, so make sure we're kind of aware. You don't have to memorize these percentages, but you should know this 81%. That's kind of a big thing. Just realizing how much fossil fuel energy we're actually kind of dependent on. This is a graph here, a line graph. Just kind of showing us how energy in the U.S. has changed over time. This kind of takes us back to the 1850s. This is around Civil War time, and it takes us all the way through modern day. Right? You can see the different colors are showing you just all the different types of energy resources that we have available. So if you kind of look, I just want to look at a couple different areas here. For example, like in the 1870s, this is a point in time where transportation started to change in the U.S. There was a lot more steam-powered ships, a lot more trains that utilized steam. So a lot of these types of transportation utilized a lot of coal. Burn the coal, boil the water, produce the steam. So you see this black line here starting to kind of rise right around that particular point in time. Another point in time here is around the 1940s. This is kind of around the baby boom era. This is also a time when the green revolution started to crank up a little bit. Agriculture started to change. A lot of people now in the 1940s are heating their homes with natural gas instead of using wood. Before that, believe it or not, a lot of people use wood to heat their homes. So you can see here, for example, the natural gas, that yellow line is going up. That red line, that oil line, remember, people are owning a lot more cars now, so you can probably see that line goes up a lot as well. Another point here I want to just kind of make mention of is around the 1960s. This is the advent of nuclear energy. Now, nuclear energy in the United States and around the world, you'll see this kind of purple line here. That's kind of where that line eventually started to kind of come up. So a lot of places in the United States are now using nuclear power instead of coal to generate electricity. And then finally, in the 2000s, this is where we started to get kind of serious about renewable energy. So you'll notice this kind of green line right in here. It starts to kind of go up just a little bit. And you'll also notice that as that green line goes up, you can see, for example, coal going down, oil going down, and that's because we're using a lot more renewables. So hopefully that becomes more of a trend because all of these fossil fuels, the red, the yellow, and the black, that's all greenhouse gas emissions. So we've been pretty high for a while. Getting those things to come down, by possibly using renewables is kind of a good trend. So hopefully that kind of. All right, just a few more things here. Different types of energy are utilized for different purposes. I mean, for example, transportation. What kind of energy do we use? We use gasoline or airplane fuel. We wouldn't put firewood into our gas tank, right? That's kind of ridiculous. Electricity, we mainly use coal. There are some other things as well, but coal is kind of the big one. So there's a term here called energy efficiency. Energy efficiency basically refers to, how efficient the process is of not only obtaining the fuel, we have to obtain coal, but then converting that into energy that can be used for work. I mean, for example, converting that into electricity, or taking natural gas and oil and converting that into, let's say, a fuel to either heat your home or to power your car. These efficiencies are really important. Here's a really good example of energy efficiency, or I should say the lack of efficiency. This is how we obtain energy from coal. And just kind of a picturesque view of kind of what happens when we take coal from the ground, right? I mean, it's in the ground, and eventually we get electricity from that in our homes, right? And look at all these different stages that we have to just go through just to obtain it. We have to extract the energy, or we have to extract the coal. That requires energy. We have to transport the coal. That requires energy. We have to process it. We have to burn it. We have to combust it. We have to remove all the waste and dispose of that. We have to generate the electricity. We have to transmit it to your house, and then we can use it. I mean, all of these steps, we actually lose energy every single step of the way. Electricity, the generation of electricity, is only about 35% efficient. We lose 65 to 70% of our energy because of all of these processes that are involved just to obtain that electricity. So it's not a real efficient process. The more efficient it is, the better it is. There's a term here called EROEI. It stands for energy return on energy investment. And basically what it is, it's a fraction. It's a mathematical fraction. The numerator is a number that represents the energy that we can obtain from a fuel source, whether it be coal or natural gas or whatever it is. And we divide it by the energy that we invest just to obtain that fuel. So here's just a good example. I think this will kind of help us understand. It says, in order to obtain 100 joules of coal, so this is an amount of energy that we can get from coal, from a surface coal mine, 5 joules of energy is expended. So we have to use 5 joules of energy just to obtain that 100 joules of energy from coal. So if we want to calculate the EROEI, all you have to do is do a division problem, right? 100 joules, that's the energy obtained from the fuel source, divided by 5 joules, which is the energy invested to obtain the fuel. So if you divide those two things, you get this number, 20. You might be like, well, what does that number mean? Well, this number is relative. I mean, we use it to compare it to other fuel sources and what their EROEIs are. For example, the bigger the number, the larger the EROEI, tells us that that's a pretty efficient process. It's a pretty efficient way of obtaining fuel and using fuel. The lower the number is, the less efficient the process is. I mean, for example, it's becoming. I'll use coal as an example. It's becoming a lot more difficult to obtain coal, process it. It's becoming harder because we're running out of coal, right? I mean, we have to invest more energy. So think about what that's going to do to the denominator here. If we have to invest more energy, that denominator is going to go up. So, I mean, imagine if we took this fraction here, and instead of 5 joules of energy, we changed it to 10. Well, the numerator is not going to change. We still can get the same amount of energy from coal. But now that we're exerting more energy to obtain it, it's going to decrease our EROEI. And when that number goes down, then we got to start getting serious about maybe finding some alternative ways to use fuel. So finding some alternative fuel sources, and that's what we're starting to do. Is this EROEI for a lot of our fossil fuels is becoming too high, or I should say, becoming too low because we're investing a lot more energy in order to get those things. So make sure we know what this is. It's an easy, I think, mathematical calculation to do, but make sure we kind of understand what that number actually represents. Our last two things, real quick. I just want to talk briefly about transportation. I mean, obviously, in the United States, for example, we use a lot of energy in transportation. 30% of all the energy in the United States is just used for us to get from point A to point B. Now, how do we travel? Car, bus, motorcycle, airplane, whatever. There's different methods of transportation, but pretty much every single one of them utilizes a lot of petroleum, a lot of oil, a lot of gas, which does produce greenhouse gases. Just want to point out one thing on this little chart here. They give you these different modes of transportation, and they tell you kind of the average amount of energy in megajoules. This is a unit of energy per passenger for every kilometer that's driven. A kilometer is a little bit longer than a mile, but anyway, the one number that kind of stands out is this one: a passenger car driven alone in the United States. That is a very common form of transportation. It's actually much more common than a lot of other countries around the world. A lot of people are driving cars and they're the only ones in the car. Like for example, if you drove to school today, okay, chances are most of you just drove by yourself, right? You could have had maybe three other kids in the car with you. Maybe you picked up your neighbor or the kid across the street or whatever, but maybe they drove their own cars to school, right? So what I'm looking at is this number, which does contribute to greenhouse gas emissions. We can actually, drastically cut that number down if we just carpool more. If we had more people in a car, instead of four people in their own separate cars, that would probably be a lot better for the environment. Wouldn't you think? I would hope so. So I don't know. Maybe that's a simple thing that we can do more of in this country is just, carpool more. Instead of you driving to school yourself, maybe you drive a couple of people, or maybe you hitch a ride with somebody, or God forbid, you all get on the cheese wagon and you all take the bus to school. But that's not that cool. Nobody wants to really do that. I understand, but whatever. All right, last thing, real quick here. I just want to take a look at fuel economy. In the United States and really around the world, this is probably true, but in the United States, SUVs, minivans, small trucks, these are the highest selling vehicles in the country, especially between 1995 and 2020. The problem with those types of vehicles is they tend to have pretty poor gas mileage, pretty poor fuel economy. A lot of those vehicles have less than 20 miles per gallon. They're getting a little bit better. Today, maybe some are a little bit over 20, but a lot of those vehicles, especially older ones, they get less than 20 miles per gallon. So that means every gallon of gas, might get you about 20 miles. Whereas a car, gets you close to 30. So there's another kind of simple thing that we can maybe do is, when you buy a car, maybe we should look at fuel economy. Because if the higher the fuel economy or the higher the miles per gallon, you're burning less gas to travel the same distance as another car that might have a lower fuel economy. But here's what I look at too. It's like when you go and buy a car, is gas mileage, fuel economy the only thing that you look at? Come on. I mean, it's not. I mean, it's not like you walk into a car dealership and say, "Give me your car that has the lowest, or I should say, the highest fuel economy, the highest miles per gallon." Most people probably don't do that, but I think we're starting to look at that a little bit more with the environmental issues we have. But of course, we're concerned with the color of our car and how fast the car goes and how cool it looks and does it have power windows? I mean, all these bells and whistles we look at as well. But fuel economy is probably something that we need to look at a little bit more closely, especially if we're concerned about the environment. All right, guys, that's it for today. That was quite a bit. Just make sure you check Buzz for the assignments for this particular topic, and I will see you soon. Take care, everybody.